Hi everyone, welcome back in this video. Uh, Today, what we are going to understand the four important topics in the electromagnetic waves. Very often people feel very confused about these terms, but I believe that after watching the whole video, you will be able to differentiate all the terms very easily, and both conceptually and both mathematically as well. Okay, let's go with the term energy density. Then after that we'll go to the average energy density, then energy flux density, and then intensity, and this one is also called the pointing vector. So let's go one by one. Let's try to understand first energy density. Energy density. Since we know when electromagnetic wave, so here I have given an electromagnetic wave which is traveling along the z-axis. So this is the propagation. A wave is propagating along the z-axis, and electric field is varying along the x-axis, which I took this axis. So x direction is polarization. So a wave is polarized along the x-axis. So basically, I repeated it so many times that electric field will decide the direction of the polarization. The direction in which the electric field is varying or oscillating is said to be the direction of the polarization. And since you can see from the above like diagram, we can see electric field is varying along x-axis. I call this as the x-axis. Okay, so polarization is along the x direction, and wave is propagating this direction, which I took as the z-axis. So wave is propagating along the z direction. And now we can represent the solution to the wave equation in terms of electric field and the magnetic field. So we can write the electric field equation as E equals E naught, and this electric field is along x-axis, and course of wave is propagating along z-axis, kz minus omega t plus delta. Okay, so this is the electric field, and similarly magnetic field is given by E equals B equals B naught. That must be along the y-axis, because there remains only the y-axis, cos of kz minus omega t plus delta. Okay, this phase will tell us the direction of the propagation. Okay, I hope you have seen the videos, but if you haven't seen, that's completely fine. We can proceed with that. I hope you know all you know these two things. These two things are the basic equations, where B naught is actually E naught by C. Okay, these are certain fundamental things. Okay, now let's proceed. What is the energy density? Now when this electromagnetic wave propagates in the space, so we call this an electromagnetic field. So when I call as electromagnetic wave EM wave, what I mean is electromagnetic field, electromagnetic field, because finally electromagnetic wave is actually composed of electric field and the magnetic field. So like when it propagates through the space, both electric field and the magnetic field propagates through the space, and obviously they must carry some energy in the space. So if I take some unit volume, in the space, unit volume, let's assume 1 centimeter cube in some space. Let's assume like there is some simple unit volume I took in the space, in which the direction, in the direction, it should the wave should pass through this volume. Okay, the wave should pass through this volume. Okay, so this is actually 1 centimeter, 1 centimeter, and the 1 centimeter. So this is the unit volume. So when electromagnetic passes through this unit volume, how much energy does electromagnetic have, per unit volume? How much energy? It's very simple. How much energy? How much energy? How much energy is present per unit volume of electromagnetic field? Or simply, if I took some unit volume of the electromagnetic wave, how much energy is present in that in that volume, that is called the energy density. Okay, simply energy density is energy per unit volume of EM field or EM electromagnetic wave. Now we know that energy is present both in the electric field and the magnetic field. So actually it is represented by, generally most of the books are represented by U, but maybe some other books represent it with a different term, but like most of the books use it, U equals 1 by 2 epsilon 0 E square plus mu 0 by 2, I'm sorry, 1 by 2 mu 0 B square. So this is actually energy density. This is U is actually energy density. You can easily see there are two terms, this term and this term. So 1 by 2 epsilon 0, 1 by 2 epsilon 0 E square is energy per unit volume present due to electric field component, due to electric field component, because electromagnetic have it has both electric field and the magnetic field component. So this part is due to the electric field contribution, and 1 by 2 mu 0 B square is energy per unit volume present due to the magnetic field component. Magnetic field, because when we take the one unit volume, any 1 unit volume somewhere, okay, so both electric field and the magnetic field should be there because it is actually oscillating. Okay, let's take here somewhere like unit volume here. Okay, so both electric field and the magnetic field is present there, it is actually oscillating there. Okay, so simply electric field contribution is this much and magnetic field contribution is this much, so this is actually the energy density. Now since the energy density, this energy density U, it contains actually, it contains E square and B square. Okay, and we know E itself contains cos, so E square itself contains cos square, and B itself contains cos, and so B square also contains cos square. And we know actually, so both these two terms contain cos square in it. Okay, cos square of kz minus omega t plus delta, both. And we know this cos square is actually sinusoidal. That means varying. Okay, so when we say we must, so whenever there is some sinusoidal term, so we have to take the average. Okay, we have to take the average, and we have to take the average value in one complete cycle. So what is the average value of energy density in unit volume? Because I know, I hope you understand now why we take the average, because E square contains cos term, B square contains cos term, which is actually sinusoidal in nature. So taking into consideration the sinusoidal in nature of E square and the B square, so we must take the average value of U. So average value of U is equal to 1 by 2 epsilon 0 average value of E square. It's simple, plus 1 by 2 mu 0 average value of B square. Isn't it simple? So we took average value because E square and the B square contains a cos square term which is sinusoidal in nature. So average value will make sense now, because it's not something which is fixed. Okay, because it's varying, actually it's oscillating, both electric field and the magnetic field is oscillating, and cos term does take care of that thing. Okay, so 1 by 2 epsilon 0 E square from here, so it would be E naught square, then average of cos square kz minus omega t plus delta plus 1 by 2 mu 0, it would be b naught square and average of cos square kz minus omega t plus delta. Okay, and we know average of the cos square is 1 by 2, so this is also 1 by 2, so 1 by 2 epsilon 0 e naught square 1 by 2 plus 1 by 2 mu 0 b naught square 1 by 2. I hope you understand it clearly, because average of cos square is 1 by 2. And if you try to solve this thing, so what it would become, so it would become epsilon 0 e naught square by 4 plus epsilon 0, no, sorry, not epsilon 0, b naught square by 4 mu 0. So this is the average contribution to the electric field component. This is the average contribution due to the magnetic field component. I hope you understand it. We can represent this term as average of UE. In some books you can see it, and this can you can represent as average of UB, average of the magnetic field. It's simply, so average of UE is this term, average of UB is this term. So there is some mathematics we can see that actually this and this are equal. So we use some basic mathematics. Let's try to understand what is average of UB. So average of UB is b naught square by 4 mu 0. Okay, I hope you know it. Let's use the basic definition of speed of light, which is c equals 1 over root of mu 0 epsilon 0. Okay, which implies c square equals 1 over mu 0 epsilon 0. There is no problem in taking that. Now what we do, we can calculate the value of mu square here. Okay, mu square equals 1 over c square epsilon 0. We can substitute that here, so it would become b naught square by 4. In place of mu 0, what do we use? 1 by c square, so it would be epsilon 0 c square. There is no problem in doing that. And we also know that b naught is actually e naught by c. Okay, we can substitute that here, so it is e naught square by c square. 4 is there, and epsilon 0 c square will go, so it became 1 by 4 epsilon 0 e naught square. Okay, it's this thing, isn't it? This thing, it's average of UE. So finally what we got is that total average energy, that is average energy per unit volume of an electromagnetic field or electromagnetic wave, is actually average of UE plus average of UB, but this is equal to this thing. Okay, so we can write it average of UE plus average of UE. So it's like 2 times average of UE, and 2 times, what is average of UE? Average of UE is 1 by 4 epsilon naught e square, e naught square. So this will go with this, so average of U equals 1 by 2 epsilon 0 e naught square. Okay, so this is the average of U. Or you can represent it in terms of average in terms of in terms of b naught. Okay, how? You can here substitute in this term. You can substitute epsilon 0 value, then using again this equation, writing e naught as this c b naught, we can also write average of U equals 1 by 2 mu 0 b naught square. I hope this makes sense now. So this is actually these two terms, energy density and average energy density. And I hope you understand now the difference and why we take the average. Now let's go to the energy flux density. Energy flux density. Energy Now third term is energy flux density. So basically energy flux density has another name, which is actually Poynting vector. Poynting vector. So what it says actually energy per unit area per unit time, energy per unit area per unit time transported by the field, okay. Let's assume this wave is traveling now. Let me copy it from here. Okay, copy. Let me put it here. Let's assume now this wave is traveling in the space. This wave is traveling in the space now, and there is some surface. Okay, there is some surface I put, and I took 1 centimeter square area of the surface, and I see in 1 second, like 1 second, I take into consideration, and how much energy is transported uh, by this electromagnetic wave or the field through this 1 centimeter square area in 1 second. So how much energy is transported by the electromagnetic field in 1 second through this 1 centimeter square? Okay, that is energy per unit area per unit time transported by the field. That is the meaning of the Poynting vector. That is actually S. Okay, and S we know is actually 1 over mu 0 E cross of B. It's very simple. It's very simple. And I hope now you get that this must be somehow connected. This must be somehow connected to energy density as well. Why? Because energy density is somehow energy per unit volume. So if that energy per unit volume is moving with the speed of light, so S must be connected with somehow C times U, because if energy per unit volume is U, energy per unit volume is U, and that is moving with the speed of light C. So if I am here and measuring through the 1 centimeter square area in 1 second, so it must be somehow connected with the C and U, and we'll see the relation. Actually, we'll prove that relation probably in this video. Hopefully this video doesn't gets too much lengthy, but this is the physical meaning of the Poynting vector. Okay, so basically 1 over mu 0 E cross B, or the Poynting vector will give us the energy per unit area per unit time transported by the field. Okay, and now since we know from these two equations that electric field is actually given by E naught x cap cos of kz minus omega t plus delta, there is no plus delta, there is no problem in taking this thing, and B is actually B naught y cap cos of kz minus omega t plus delta. Now you can see x cross y, because if you substitute here E naught and the B naught here, so S vector, S Poynting vector will give us somehow 1 over mu 0. There will be E naught, there will be B naught, and there will be cos term, cos square kz minus omega t plus delta. And obviously if you try to solve this x cross y, so that will give z cap. Okay, that will give z cap. So Poynting vector must have the direction of the propagation, so that will give z cap. Okay, I'm not interested in z cap right now, but I'm interested in this thing. So that will give me 1 over mu 0 E naught B naught cos square kz minus omega t plus delta. Okay, this is the magnitude of the Poynting vector. Now again, so this is and what is the direction of this thing, which is z cap, which is actually the direction of the propagation. Okay, and you can see from here it's x cap cross y cap, that should be equal to the z cap. Okay, x cap y cap, x cross y will give z cap. Okay, y cap cross z cap will give x, z cap cross x cap will give y cap. Okay, so this is the what we call as the energy flux density or the Poynting vector. Now again, you can see there is again cos square there, so which is actually oscillating. So what we do, we take the average. So we must take the average of this Poynting vector. That would make now the sense, because again, this is oscillating. This is not somehow constant, but rather it's varying, and we must take into consideration one full period. Okay, one whole cycle. So let's take average of the Poynting vector. Average of the Poynting vector, which is actually called the intensity. So if somebody calls you what is the intensity, so it is actually the average of the Poynting vector. And what is Poynting vector? Poynting vector, you know, it's energy per unit area per unit time transported by the field. Okay, so let's take the average. Let's take the average. So average of the Poynting vector equals 1 over mu 0 E naught B naught average of this cos square kz minus omega t plus delta. So again, average of cos square is 1 by 2. So average of the Poynting vector becomes 1 over mu 0 E naught. Why I wrote this cos b square? I shouldn't wrote it. Okay, I shouldn't write it. So b naught, and what is average of the cos square? It is 1 by 2. So average of the Poynting vector, which we call as the intensity, equals 1 over 2 mu 0 E naught B naught. I hope you get it. Okay, but we know B naught is actually E naught by C. There is no problem in that. We know this thing. So intensity will become average of the Poynting vector equals I'm very sorry, 1 over 2 mu 0 E naught, and it's E naught by C. There is again no problem in that. Okay, so it becomes 1 over 2 C mu 0 E naught square. Is there any problem? Okay, no problem at all. So we use again some equation. Speed of light is given by 1 over root of mu 0 epsilon 0. Now if I take square, c square is given by 1 over mu 0 epsilon 0. Do I have any problem in that? No problem. We can replace this mu naught, which implies mu naught is given by 1 over epsilon 0 c square. There is again no problem in doing that. So let's substitute that thing here. So intensity would become average of the Poynting vector equals 1 over 2 c in place of the mu 0. Why replacing the mu 0? Because we're dealing with electric field. So we must be interested in epsilon 0, not in the mu 0, because mu 0 is magnetic permeability. Okay, so that's why we replaced this mu 0 by the epsilon 0. So mu 0 is given by epsilon 0 c square. So it goes up, and a naught square does something cancels. Yeah, cc will go. So 1 over 2 epsilon 0 e naught square. Okay, if you see somehow what we get something like here, average of energy density. That is why I told you that it would be connected to that thing. So intensity would be given by the average of the Poynting vector, that is equal to 1 by 2 epsilon 0 e naught square. And we know if we write it like this, let's see how we write it. But there must be some c. Yeah, c is there. So c is there. Okay, so c is there. So intensity equals average of the Poynting vector, which is equal to c times this is average of energy density, average of the energy density, this average of u. So average of u, I hope you get it. So we can write there then intensity equals speed of light, c times the energy density. Energy density. So like this is, I think this is enough for the video. That's why I told you back that how much energy passes through this surface, that would depend upon the that would depend upon the energy density and the speed of light. Its speed, okay, its speed that will define the Poynting vector actually, or the average of the Poynting vector. This is c times average of u, and we also know that average of u here, average of u is also 1 by 2 mu 0 b naught square. We can write intensity in some, in some examination it might give you c times 1 by 2 mu 0 b naught square, because we know these two are equal. So these two formulas, this formula, these are very important. So I hope you get these four terms now. There is no problem in that. This term, this term, this term, and this term. Thank you so much. Thank you for watching.